I am going to discuss the concept of energy and potential in an electric field. So here we have pictured an electric field pointing to the right. We know that if we put a charge Q in an electric field, it will experience a force given by Q times the electric field. And this arrow here indicates that force pointing to the right. Now if I take this charge Q and move it perpendicular to the electric field, it takes no force to move that charge because the force due to the electric field is at a right angle to the direction we're moving. So we're doing no work, so the potential energy is not changing for that charge Q. This would be like being on a hill and moving laterally. That is not changing your elevation. So there is no change in the gravitational potential energy. Now if we take this charge and move it as indicated by this displacement vector here, it takes a force to do that. We have to overcome the force due to the electric field. And so we are doing work. And so the potential energy of that charge is increasing as we move it to the left. This would be like moving uphill and increasing gravitational potential energy. Now, if we let the charge go, there's a force due to the electric field, so it will accelerate to the right. And so it is gaining kinetic energy. So the electric field is doing work on the charge and converting the potential energy into kinetic energy as the charge moves to the right. So here's our charge in an electric field, and the electric field does not have to be uniform for what we're discussing here, but at this point this charge would experience a force due to the electric field given by this arrow here. Now I'm going to take this charge and displace it along d sub L in the direction indicated. Now it is going to take some force to displace it. Although I'm not going directly against the electric field, it's still taking some force to move along dl, and I want to determine how much work that is required to do that. Now I can think of this displacement dl as the two displacements, one directly against the electric field and then one perpendicular to the electric field. So now when we move perpendicular to the electric field, as we discussed earlier, we are doing no work. So all the work that is occurring is along this displacement right here. And this distance right here will be d sub L times the cosine of this angle right here, which is 180 degrees minus theta, where theta is the angle between the electric field and our actual displacement. So this length right here is given by dl times the cosine of 180 minus theta. So the work done is the force I'm applying. The force you're applying along this length here is Q times E, because you have to overcome the force of the electric field, and the distance is dl cosine of 180 minus theta. Okay, so the work would just be the force through that distance. Now cosine of 180 minus theta is minus the cosine of theta. And now we can recognize that the magnitude of the electric field times the magnitude of this displacement dl times the cosine of the angle between them is just the dot product between the electric field and our differential displacement dl. So the differential work is minus Q times the dot product of the electric field and our differential movement, dl. So now let's take our charge Q and move it from position A to position B along the path shown. So we can think of this movement as a combination of all these little d sub L movements. And we know for each individual movement d sub L, the work that's being done is minus Q E dot dl. So the work to go from A to B would be the sum of all these differential works, dw, or the work is minus Q times the integral from our initial position A to our final position B of E dot dl. Now, potential is the amount of work that is done if you're moving 1 coulomb of charge. So the potential difference between points B and points A will be the amount of work divided by Q, or minus the integral of E dot dl from position A, your initial position, to position B, the final position. I have now indicated a second path from A to B, and let me call that path 2, and our original path is path 1. Now, let's suppose that in going along path 1, it takes 1 joule of work to go from A to B, and that going from A to B along path 2 takes 2 joules of work. Now, we know if we go in the opposite direction then, along path 2 from B to A, that the field is doing work, and we would extract 2 joules of energy from the field. So, what that would mean then is if we would go from A to B along path 1, we would expend 1 joule of energy, we would do 1 joule of work, and coming back from B to A along path 2, we would extract 2 joules. So overall, we would gain a joule of energy. Now that would be a violation of conservation of energy. So this is indicating that the integral of E dot dl from A to B is going to be independent of the path we take. We always will have to get the same value. And a way we indicate that is putting this little circle on the integral of E dot dl, which indicates that when we do this integral, we're doing it along a closed path, and we'll come back to our original position. And in order for energy to be conserved, that will have to equal 0.